Hello everybody, welcome into another lesson. So today we are going to talk about methods for evaluating limits. We are going to talk about three methods today called direct substitution, which is the first method we should always try. The next method we'll talk about is called factoring. And then after we factor, we'll use direct substitution. And then in the case where neither of those work, we'll also use what's called a conjugate method. And then later in the course, once we've learned derivatives, there's actually a fourth method called L'Hopital's rule, but we're not going to do that one today. But getting started here, direct substitution is definitely the easiest. I have the limit as x approaches negative 2 of the function 3x to the fourth plus 2x squared minus x plus 1. If the function is defined at the value of x you're taking the limit of, you can use direct substitution. And this is a polynomial. All polynomials they have the domain of the entire set of real numbers. So we can just plug that negative 2 right into x. So let's go ahead and do that. So we can take then 3 times that negative 2 to the fourth plus 2 times negative 2 to the second minus negative 2 plus 1. That would give us 3 times 16 plus 2 times 4 minus 2, that's plus 2, plus 1. So that would end up giving us 48 plus 8 plus 2 plus 1. So 48 plus 8 is 56, plus 2 is 58, plus 1 is 59. So the limit as x approaches negative 2 of this function would be 59. So as x approaches negative 2, your y value is going to approach 59. So direct substitution is definitely the easiest way to go, if at all possible. Let's do another by direct substitution. Let's say we have the limit as x approaches positive 2 of 2x squared plus 1 all over x squared plus 6x minus 4. Alright, so we have 2x squared plus 1 all over x squared plus 6x minus 4. Well, we should first try direct substitution. So let's go ahead and do that. We'll substitute that 2 in for x. So that would give us 2 times 2 squared plus 1 all over that 2 squared plus 6 times 2 minus 4. Well, this would turn into 2 times 4 plus 1 all over 4 plus 12 minus 4. So this would equal 8 plus 1 over 4 plus 12 minus 4, which would simplify into 9/12, which we know 9/12 would reduce to 3/4. So the limit as x approaches 2 of this function is going to be 3/4 by direct substitution. Let's do one more of direct substitution, then we'll move on to the next method. So let's see here. We're going to take the limit as t approaches negative 1 of the quantity of t squared plus 1 to the third power times the quantity of t plus 3 raised to the fifth power. So we're taking the limit of this entire function. Well, again, we can use direct substitution because polynomials, you have the entire the domain's the entire set of real numbers, so we can use direct substitution here. So doing that will end up giving us, if we take -1, put that in for t, that'll give us -1 squared plus 1, all that raised to the third power, times that -1 plus 3 raised to the fifth power. Well, okay, so this is going to turn into -1 squared. Well, that would be +1 plus 1 raised to the third power times -1 plus 3 raised to the fifth power. Alright, well, 1 plus 1 is 2. This turns into 2 to the third power. Then -1 plus 3, that turns into 2 raised to the fifth power. Well, 2 to the third times 2 to the fifth is 2 to the eighth power. Which, what is 2 to the eighth power? Well, 2 times 6 is 64, 128 for 2 to the seventh, so this would be 256. So the limit of this function as t approaches -1 is going to be 256. Alright, so those were some easy direct substitution cases. Now, what if I gave you something like this? So, what if I gave you the limit as x approaches 2 of x squared minus x plus 6 all over, sorry, x squared plus x minus 6, that would make more sense, all over x minus 2. So what if I gave you the limit as x approaches 2 of x squared plus x minus 6 all over x minus 2? Well, we know if we do direct substitution, you're going to get a denominator of 0, which will make this undefined. That doesn't mean the limit doesn't exist. If direct substitution fails, the next method you want to try is by factoring. So let's see if we can factor this. We'll keep the limit notation for now since we're not ready to do any substitution yet. So let's see if we can factor the numerator. That should actually factor into the quantity of x minus 2 times x plus 3. Divide that by the x minus 2. Well, what do you know? Between the numerator and denominator, you can factor out an x minus 2. This will reduce this down to the limit as x approaches 2 of x plus 3. Now we have this in a form that we can use direct substitution. So the idea of factoring is to get it into a form where we can use direct substitution. So now we have it reduced to the limit as x approaches 2 of x plus 3. Let's apply direct substitution. Well, this will just turn into 2 plus 3, which would give you the limit to be 5. So the limit of this function as x approaches 2 is 5. And if you were to look at this graphically, let's say you put this into a graphing calculator, you would see that as x approaches 2 from both the right and left hand side, your y value will approach 5. So factoring is a very good strategy. Alright, let's see here. We have the limit as x approaches -4 of x squared plus 5x plus 4 all over x squared plus 3x minus 4. So we have the limit of this function. We have the limit as x approaches -4 of x squared plus 5x plus 4, all that divided by x squared plus 3x minus 4. Well, let's try direct substitution first. If you put in -4 for the denominator, and here's a clue. If you have a denominator, you should check and see if you're going to get an undefined value by direct substitution. That should be the first thing you check for. So -4 squared is 16, and then 3 times -4 is -12, so 16 minus 12 is 4, minus 4 is 0. So we do in fact get an undefined value because direct substitution will give you a denominator of 0. But if we can't do direct substitution, our next approach should be to try to factor both the numerator and the denominator. So let's keep that limit notation for a minute. The limit as x approaches -4 of, let's factor the numerator, this would end up becoming the quantity of x plus 1 times x plus 4. Divide all that by x minus 1 times x plus 4. And you got your factored numerator and denominator. Now notice you can cancel out a common x plus 4 between both the numerator and denominator. So this will reduce to the limit as x approaches -4 of x plus 1 divided by x minus 1. Now we have this in a form where we're not going to get a denominator of 0. We can do direct substitution. So let's put in that -4. So -4 plus 1 divided by -4 minus 1. Well, that's going to give you -3 over -5, which would give you 3/5. So the limit as x approaches -4 of this function would end up being 3/5. Let's do a few more factoring because some of these can get a little funky. Let's say I give you the limit as x approaches 1 of x cubed minus 1 all over x squared minus 1. So you have the limit as x approaches 1 of x cubed minus 1 divided by x squared minus 1. Well, if you do a direct substitution, you would get 1 minus 1, which is 0 in your denominator, so direct substitution isn't going to work. That means we should next switch to factoring, see if that's going to work. So let's go ahead and try to factor this. So the limit as x approaches 1, let's factor the numerator. That should factor into the quantity of x minus 1 times the quantity of x squared plus x plus 1 divided by your denominator. You factor that, you should get x minus 1 times x plus 1. Well, what do you notice? You have a common x minus 1 that'll cancel out between the numerator and denominator. So let's rewrite this now in its factored form. The limit as x approaches 1 of x squared plus x plus 1 divided by x plus 1. And if you direct substitute now, you won't have a denominator of 0. This will not be undefined. So we can now use direct substitution. So let's put 1 in for x. You would get 1 squared plus 1 all over 1 plus 1, which would give you 1 plus 1 plus 1 all over 1 plus 1. Well, the numerator would turn into 3, the denominator would be 2. So the limit as x approaches 1 of this function is going to be 3 over 2. Let's do a couple more here. Now the next couple actually tie into derivatives. Though I'm not teaching you derivatives today, it's important you see this. So let's see here. I have the limit as h approaches 0 of 4 plus h quantity squared minus 16 divided by h. So I have the limit as h approaches 0 of 4 plus h quantity squared minus 16 all over h. Well, as it turns out, we're going to later discover this would be the derivative of x squared at x equals 4. But we're not there right now. But I'm going to show you how this works. So we know if we do a direct substitution at h equals 0, we'll get a denominator of 0. That's definitely not going to work. So we need to expand out the numerator. So this will turn into the limit as h approaches 0 of, take the 4 plus h to the second power, you would get 16 plus 8h plus h squared minus 16, all that divided by h. Well, your 16s cancel out. You would have the limit as h approaches 0 of 8h plus h squared divided by h. Well, notice in the numerator you can factor out a common h. You'll have the limit as h approaches 0 of h times 8 plus h divided by h. And now you can factor out an h between the numerator and denominator. This would just turn into the limit as h approaches 0 of 8 plus h. And you can now use direct substitution. So put in 0 for that h, you get 8 plus 0, or 8. So the slope of the line, or also known as the derivative of x squared at the point x equals 4, would be 8. So the limit of this function as it approaches 0 is 8. You don't have to know derivative today. I don't expect you to know that, but be prepared in the near future to see problems like that. We're going to have a lot of these with derivatives when we get into that, which will probably be sometime next week. Okay, let's do another one like it. Let's do a little bit of a higher power. Let's take the limit as h approaches 0 of 2 plus h to the third power minus 8 all over h. So we're going to take the limit as h approaches 0 of 2 plus h quantity cubed minus 8 over h. Again, direct substitution isn't going to work. You'll get a denominator of 0. So we need to expand out that binomial in the numerator in order to be able to have any hope of factoring. So this will turn into the limit as h approaches 0 of, this would definitely start out as 2 cubed plus 3 times 2 to the first, 3 times 2 to the second times h to the first plus 3 times 2 to the first times h to the second plus h to the third, all that minus 8 divided by h. So all I did was I expanded 2 plus h to the third power. This will simplify into the limit as h approaches 0 of 8. Alright, so plus, now 2 squared is 4 times 3 is 12, so that'd be plus 12h. And then 2 to the first is 2 times 3 is 6, so this would be plus 6h squared plus h cubed minus 8, all that divided by h. Well, your 8's cancel out. 8 minus 8 is 0, so you're left with all h terms. You'll have the limit as h approaches 0 of 12h plus 6h squared plus h cubed, all that divided by h. And then if you go ahead and factor out a common h, you would end up having h times the quantity of 12 plus 6h plus h squared, all that divided by h. Notice you can factor out a common h from numerator and denominator. I should say this is the limit as h approaches 0 of this. I forgot the limit notation. So this will end up being the limit as h approaches 0 of 12 plus 6h plus h squared. Now we have a form we can use direct substitution. Just put the zeros in for h, you just get 12. So your limit in this case is going to end up going to 12. So the limit of this function would in fact be 12 as it approaches 0. Alright, so we've seen direct substitution. We have seen factoring, which turns into direct substitution after we factor. The next method we're going to discuss today is called multiplying by the conjugate, which is probably the last method you should pick. That is a method that should probably be your last choice by default. So we talked about factoring. Let's see. The next one is called the conjugate method. Alright, so what do we got here? Let's say I give you the limit as t approaches 9 of 9 minus t all over 3 minus the square root of t. So we have the limit as t approaches 9 of 9 minus t all over 3 minus the square root of t. Now, in theory, we could factor the numerator and have radicals in it, but in general, if you have radicals, you want to get rid of them. If we recall from algebra, the way to get rid of a radical from the denominator, or in some cases even the numerator, you need to rationalize, which means multiplying by its conjugate. Because if you put in t equals 9, you put in 9 for t, you would get 3 minus the square root of 3, which is 0. So direct substitution isn't going to work. Factoring is not your best choice, so the conjugate method is going to come into play. So here's what we're going to do. I'm going to multiply both numerator and denominator by the conjugate of 3 minus the square root of t, which would be 3 plus the square root of t, all over 3 plus the square root of t. And then let's see what happens when we do that. When you do that, you would end up getting the limit as t approaches 9 of the quantity of 9 minus t times 3 plus the square root of t, all over, if you FOIL the denominator, you would end up getting 9 minus t. So we've just dealt with the conjugate method, but we're still not done yet. If you do direct substitution into the denominator, you'll get a denominator of 0. So we've done the conjugate method. This is going to break down into factoring. And we see that we can factor out a 9 minus t from the numerator and denominator. Those will cancel out. So what you're left with is the limit as t approaches 9 of 3 plus the square root of t. Now we have a form we can do direct substitution. So the idea is, if you need to, you'll apply the conjugate method first. The hope is to get it into something you can factor. Once you factored, then you can use direct substitution. So you're really doing all three in one. But the square root function is defined for when t equals 9, so we can do direct substitution. You would end up getting 3 plus the square root of 9, which would turn into 3 plus 3, or simply 6. So the limit of the original function actually turns out to be 6. And if you put this part in graphically, you would actually see your y value approaches 6 as you approach a t value of 9 or an x value of 9. Let's do a few more conjugates, because I know conjugates can get a little bit funny. Alright. We have the limit as h approaches 0 of the square root of 1 plus h minus 1 all over h. Alright. So we have the limit as h approaches 0 of the square root of 1 plus h minus 1, all that all over h. Well, direct substitution's not working because you put in 0, you'll have a 0 in the denominator. Factoring isn't even going to work. There's no way to factor this. So the only other possible method is going to be the conjugate method. In this case, we need to rationalize the numerator. You will sometimes have that. And the goal with using the conjugate is to get something you can hopefully factor out. Because the idea is conjugate will break down into factoring, which will then break down into direct substitution. So let's multiply numerator and denominator by the conjugate of this radical expression. So the conjugate will be the square root of 1 plus h plus 1 all over the square root of 1 plus h plus 1. Well, let's see what we get here. If you FOIL out your numerator, you'll end up getting here, we'll keep the limit as h approaches 0, you would get 1 plus h minus 1 all over h times the square root of 1 plus h plus 1. Well, 1 minus 1 is 0, so what you're left with in the numerator is the limit as h approaches 0 of h all over h times the square root of 1 plus h plus 1. And now notice between numerator and denominator, you can factor out an h. So we've started with the conjugate, we've now reduced down to factoring. We can factor out an h, which would give you the limit as h approaches 0 of 1 all over the square root of 1 plus h plus 1. And if we look at this, we can use direct substitution because we'll have a defined denominator. So let's do direct substitution. This would give you 1 over the square root of 1 plus 0, all that plus 1. Well, that's just going to give you 1 over the square root of 1 plus 1, which would give you 1 over 1 plus 1, which would just give you 1/2. So the limit of this function is actually going to end up being 1/2. So what started out looking hopeless turned out to be a nice answer of 1/2. All right. Let's see here. What else do we got? We have the limit as x approaches 9 of x squared minus 81 all over the square root of x minus 3. So we have the limit as x approaches 9 of x squared minus 81 all over the square root of x minus 3. Well, we have a radical, in the denominator, and we know that if we stick in 9 for that value of x, you'll get 3 minus 3, which will give you a denominator of 0. That's a big no-no. So we need to try to make this radical disappear. Let's multiply the numerator and denominator by the conjugate. So what you'll end up getting then is multiplying by the square root of x plus 3 all over the square root of x plus 3. So this would turn into the limit as x approaches 9 of, you would end up getting x squared minus 81 all over, you FOIL out your denominator, you would get x minus 9. And actually I forgot to multiply the numerator by that square root of x plus 3. That's okay though. At least we caught it. Well, here's the thing. The denominator, if I stick in that 9 for x, I'll still get a denominator of 0. Is there a way to factor this out? Well, we know that x squared minus 81 is a perfect square binomial. We can definitely factor that. That would give you the limit as x approaches 9 of, let's see, x plus 9 times x minus 9 times the square root of x plus 3 all over that x minus 9. And now notice we have a common x minus 9 that'll factor out between the numerator and denominator. So let's rewrite this. You would get the limit as x approaches 9 of, let's see, x plus 9 times the quantity of the square root of x plus 3. And we have a form we can do direct substitution. So let's put in that 9 for x. You would get 9 plus 9 quantity times the square root of 9 plus 3. So that's going to give you then 18 times 3 plus 3, which would equal 18 times 6, which is going to be 108. So the limit of this function is actually going to be 108. Alright, now let's get into some complex fractions. Let's play around with some complex fractions a little bit here. We have the limit as x approaches -4 of 1/4 plus 1 over x all over 4 plus x. So we actually have a complex fraction for this function. The limit as x approaches -4 of 1/4 plus 1 over x, that's all your numerator, divided by 4 plus x in your denominator. Well, I think it's definitely safe to say we're not going to be able to do direct substitution. You would end up getting 0 over 0. That's undefined. But let's look at the numerator. We definitely need to get a common denominator for the numerator. You have two denominators of 4 and x, so that means the common denominator would be 4x. So this would turn into the limit as x approaches -4. Multiply the first term by x, this would give you x over 4x. Plus, multiply the second term by 4, so plus 4 all over 4x. All that divided by 4 plus x. We're still not there just yet. Let's take the limit as x approaches -4, and we can, since we have the same denominator in the numerator, we can combine these. You would end up getting 4 plus x all over 4x all over 4 plus x. And you're probably starting to see where we're going with this. And we have a complex fraction, so let's invert and multiply. This would turn into the limit as x approaches -4 of, let's see, so 4 plus x over 4x will stay the same. But we have 4 plus x in the denominator, so this would be the same as multiplying by 1 over 4 plus x. And now your 4 plus x's will cancel between the numerator and denominator. This will turn into the limit as x approaches -4 of 1 over 4x. And we can now do direct substitution into this function. That would just give you -1/16. So the limit of this original function actually turns out to be -1/16. Let's do a couple more complex fractions. Or other types of fractions, I should say. All right. We have the limit as t approaches 0 of (1 over t minus 1 over t squared plus t. So we have the limit as t approaches 0 of 1 over t minus 1 over t squared plus t. Well, definitely not going to be able to do direct substitution. You would have 1 over 0 minus 1 over 0. It's undefined in both cases. Well, what I would suggest is we try to factor out the denominator of the second term. This would give you the limit as t approaches 0 of, let's see, so 1 over t minus 1 over, that t squared plus t will factor into t times t plus 1. Well, now you have two denominators. You have t and then you have t times t plus 1. So we definitely need to make the common denominator of t times t plus 1. So all we need to do is multiply the first term by t plus 1. This would give you the limit as t approaches 0 of t plus 1. Then you would just have minus 1 all over t times t plus 1. We have a common denominator now. Well, t plus 1 minus 1 just simplifies into t. So this will turn into the limit as t approaches 0 of t all over t times t plus 1. And the good news is we have a t that'll cancel out between the numerator and denominator. So this would just turn into the limit as t approaches 0 of 1 all over t plus 1, which we can now do direct substitution. That's going to give you 1 over 0 plus 1, which is 1 over 1, or simply 1. So the limit of that function actually turns out to be 1. Let's do one more, and this one's going to have a radical in it, and it's going to be two different terms with fractions. So let's see here. Let's say I pick the limit as t approaches 0 of 1 all over t times the square root of 1 plus t minus 1 all over t. Alright, well, here's the thing. We can't do direct substitution again because you would have two denominators with 0. But we see we can get a common denominator if we multiply the second term by that square root of 1 plus t. So why don't we go ahead and do that? So let's get our common denominator. So we'll have the limit as t approaches 0 of 1 minus the square root of 1 plus t all over t times the square root of 1 plus t. Now this is where it can get a bit tricky. This is definitely going to be a conjugate method, but notice you have a radical in both the numerator and the denominator. Well, if you're not sure which way to go, it never hurts to try to figure out which one to rationalize first, and if you get the wrong one, just start the problem over again. But I'm definitely going to suggest you pick the numerator, and you'll see why in a minute. And identifying which one you want to rationalize takes some practice. If you do these enough, you'll get some practice. But let's rationalize the numerator. So let's multiply by the conjugate of the numerator. That would end up being 1 plus the square root of 1 plus t all over 1 plus the square root of 1 plus t. Well, let's see what we get here. That's going to then equal the limit as t approaches 0. When you FOIL out the numerator, you would end up getting 1 minus the quantity of 1 plus t, all that divided by t times the square root of 1 plus t times the quantity of 1 plus the square root of 1 plus t. All that. And let's see what you get here. So in the numerator, 1 minus 1 is 0, you're just left with the negative t. So you would end up having the limit as t approaches 0 of negative t all over t times the square root of 1 plus t times 1 plus the square root of 1 plus t. Well, notice your t's will cancel out between numerator and denominator, so this will turn into the limit as t approaches 0 of negative 1 all over the square root of 1 plus t times the quantity of 1 plus the square root of 1 plus t. So I think we picked a winner when we rationalized the numerator, because if we do direct substitution now, we can stick that t value in and we'll get a finite value. So let's stick in 0 for t. You would end up getting negative 1 all over the square root of 1, which is 1, times 1 plus 1, which would end up giving you negative 1 over 2. So the limit of the original function actually ends up becoming negative 1/2. After you get the common denominator, do the conjugate method, factor out, then do direct substitution, you end up getting a limit of negative 1/2. Alright, so that's it for this lesson. Next lesson, we're actually going to deal with limits of absolute value functions and piecewise functions. So I hope everybody has a great day. Take care.